All right, good afternoon, folks, and welcome to another edition of the MSPE Graduate Seminar Series. It's a true pleasure today to introduce our graduate seminar speaker, Professor Soliman, who is currently head of the Department of Petroleum Engineering at the University of Houston, where he's also an endowed chair. Professor Soliman earned his master's and doctoral degrees from Stanford University, and he led about a 30-year span with Halliburton before joining the ranks of academia as a professor at Texas Tech and then at the University of Houston. He's a prolific in terms of publications, certainly, and holds many distinctions. Of those are the distinguished membership of the SPE. He's also a member of the National Academy of Inventors. I ask that attendees please mute your microphones and hold questions till the end of Professor Soliman's presentation. After that, I'll call on you if you use the raise my hand facility in Blackboard in order. Without further delay, Professor Soliman, it's all yours.
Thank you very much, Professor Yunus. I'm really glad to be here to talk to you. Hopefully next time it will be in person so I can also see you and you can see me. I usually enjoy visiting universities very much, and I have visited the University of Tulsa multiple times. 4 years ago, I gave another talk that was in person. Professor Shoham invited me, and I went to Tulsa. I have been in Tulsa many times before that when I was working for a Halliburton company. We were not too far away from you, and we visited. We did research. We did research with the University of Tulsa. We visited with professors. We sponsored the work there. So it's a real pleasure to come back. Even this time is virtual, and talk to people at University of Tulsa, professors and definitely students. Right now, I'm going to talk about a subject that we started a few years ago, is pulse power stimulation by electrical discharge and the plasma reaction. It looks a little different title, but we'll go through it. It's a very large subject. So what I'm going to give you is summary of several things. We have written multiple papers, and some of the work that I'm showing right now even has not been published yet. We're plan to publish that work in next year or so. Its work is still continuous. Before I start, I want to tell you a little bit about the Petroleum Engineering Department at UH. It's a fairly new department, especially if you compare it to your department. We are almost 6 years old. Actually, I'm the first chair of the department, and I joined UH back in 2016. So you can see it is very new. We have our own building. We call it ConocoPhillips Petroleum Engineering Building, and we are sitting in what we call it Energy Research Park or Technology Bridge. We have about 60,000 square feet and a standalone building, which is nice in some way because we have our own classrooms, we have an auditorium, our labs, everything is in one big area. We have 14 professors. Our professors, several of them similar to me, that they have the mix of industrial and academic experience. We have about 200 undergraduate students, 54 Ph.D. program, which we started that Ph.D. program after I joined the UH. So we grew very well in Ph.D. program. Master students 35. We like to have more than that. very typical petroleum engineering department that is very diversified. We have people from all over, which is, it makes it really exciting and nice. 4 of our professors are National Academy of Engineers. One, which is talking to you now, is member of National Academy of Inventors. Our being in Houston is nice because when we need an adjunct professor, you know, Houston is very large and it has a lot of industry, petroleum industry, many companies. So the adjunct professors are really experts too. So we're very lucky in that aspect. Let us go now to our subject. Before I talk about our subject, you know, there is, I would be lying to you if I tell you I did all this work. Obviously not. I supervised much of the work. I have many colleagues that contributed to this work. One is Dr. Wellen House, is an older colleague. We were working together in Texas Tech. Now he's in Houston, retired, but he still works with us. Dr. Peter Gordon from ExxonMobil. Exxon is supporting our work, and Peter does a lot of work in addition to being financing us, supporting us. He also does a lot of the work himself. Then I have 2 PhD students, Awad and Khalaf. Right now they are working on the subject. Hopefully we'll get their PhD, one probably by end of next year, and the other will be a couple of years later. Then I have several postdocs. They're also former students, as you can see, Ali Rizai, Fat Sadiqi, and August Zhao. There are 3 of them. They are former postdoc and former student because they are all working. 2 of them in the industry. August is already back in China. She is working for a company there. So let us start talking about. I want to talk a little bit about why we are working in this area, basically waterless fracturing. And we need to talk about what various types of waterless fracturing. We'll talk about it briefly. Then we get into our subject in plasma, which I will explain to you, show you some of the stuff that we have done or we are doing, and some work that we started, but there's going to be a lot of future in it, electromagnetic wave propagation as a result of the plasma discharge. We'll talk about all of that, and then eventually we'll have a brief summary. Waterless. Why waterless? Because of lack of water. You know, there is many areas that are in droughts. Hydraulic fracturing, it takes maybe when you fracture horizontal well in shell formation, taking 10 million gallons of water is not unheard of. It's fairly common. And that becomes a problem when you have a shortage of water. And you can't do away without hydraulic fracturing, I have to say that. But what we are proposing here, as you're going to see, it can supplement or help the hydraulic fracturing. So in some areas, you may not need hydraulic fracturing if you do enough stimulation. And we'll look at this in a little details. There's a lot more work that can be done in here. So generation of fractures, you can use this technique, as we are going to see. You can create fractures in different directions. You can bypass some area, damage around the wellbore. You can also improve permeability. And what we're going to show here is not just we're going to do measurements in the lab actually to see whether we can do all of that or not. And it can be fairly cost effective, we believe. Obviously, you know, I have to tell you, I'm maybe a little biased because I'm working on it, but I think it's a very, very interesting technique that needs to be taken further. When you look at waterless fracturing techniques, one may talk about explosives. And explosives were not very successful because they damage the well so much that it's really not helpful. That you may end losing permeability around the wellbore, or you lose wellbore integrity altogether. Actually, at one time, years ago, a nuclear device was used in a well. It was another idea, extending the explosive idea into an extreme. And I do not need to tell you that the idea obviously was not very good for multiple reasons. The amount of heat that is generated will make the rock glassy, so you lose permeability actually. Besides, you have radioactive, it was done in a gas well, you have radioactive gas for so many more years to come that you have to shut down a well and forget about that area. People have used gas gun, used propellant. Propellant is solid rocket fuel, and I'm not going to go into it, but the idea is when you perforate the formation, the shape charges go through the propellant, ignites the propellant as it is going through the casing and the cement into the formation. So basically the perforation is being, or the perforating gun, the shape charges, is being followed by a lot of burning propellant, a lot of gas that's very high pressure that will fracture the formation. This idea was used, started in the late 80s. It was a lot of work done in this area. We're going to compare it to what we are doing right now. With propellant is one-shot thing. You want to apply it again to some other place in the well. If you have a horizontal well, you have to pull out everything, go back again with new gas gun to start. In our case, we're going to show that we do not need to do that. So we have some operational advantage. There's extreme overbalance. There's some similarity. Where after perforation you expose the formation to highly pressurized gas. Actually, it can even carry some propellant in it, very, very light propellant, like 100 mesh sand, things of that nature, of that weight, and you can create fractures that is kind of property. They are short fractures. You're not any length like hydraulic fracture. Neither our technique. Then there are some chemical processes. Those are, most people will shy away from them because they may not be that safe. There is always a safety issue. Well, then what we're working on is the plasma pulse power, which I'm going to focus on. But before we get into it, let us describe the pressures that you would see when you run one technique or another. Hydraulic fracturing is, as you can see here, is fairly slow increase in pressure, to the extent that when I teach fracturing to students, we ask them what Young's modulus and Poisson's ratio do you use? Do you use the static or the dynamic? And the answer is static. So although it is happening fast, but it's not really that fast to be considered as the rock is reacting in a dynamic mode. The rock is actually acting in a static mode. So that's an interesting thing to remember. With explosives, you may end up having million psi or even higher, and in happening over microseconds. As we go down to gas gun or pulse power, it also in pulse power it also happens in microseconds, maybe 5 microseconds or so. So, but the pressure is not nearly as high. We're going to look at some of those. We actually in the lab we have gone up to it goes up to maybe 200 megapascal, which is 30,000 psi. So it happens fast enough that it is dynamic, and the fractures may not exactly, like the picture on the right, may not exactly follow the stress field, or be totally controlled by the stress field like hydraulic fracturing. In hydraulic fracturing, we know when we inject, eventually you fracture the rock, you break down the well bore and you fracture the rock, and the fracture propagates perpendicular to minimum stress. Here we are going to see that may not be exactly the case in here. So basically, what we are going to talk about is we are going to create fractures or improving permeability with high energy plasma pulse. So you have a shock wave being created, and we'll describe how. And we usually use water too, but relatively speaking is negligible volume of water. You know, and like in our experiment I'm going to show you, we fill the well bore with water. Well bore is 1.5 inch diameter or 2-inch diameter for a few inches. So it has water, but nothing like what we're talking about in hydraulic fracturing. So you have dynamic stress that you either fracture the formation or improve permeability. You may have multiple fractures in different directions, we're going to see, and they may not align with the maximum or minimum horizontal stresses. Actually, in some cases, you may even see some horizontal fractures. We'll see some of those experiments. Not only that, as I'm going to also show you a few slides and some work that we have done, but we haven't published yet. Actually, we have done a few years ago already. You could design the experiment to create an electromagnetic field. So you end up have electromagnetic wave moving into the rock. And we succeeded not only in measuring the field, but matching this data with numerical solution or analytical solution that we developed. And this electromagnetic field, we're starting to redo some of this work again. We have work that we need to publish first, but we have other ideas that we need to do. And it can be, it may be very beneficial in the oil industry. We're trying to get people interested in it to support it. I'm going to be talking about how many joule or how many kilojoule we're using. So I want to talk about what is a joule and what's kilojoule and how it is. 1 joule is equivalent to 0.239 calories. So we have equipment that can generate 20 kilojoule. So 20 kilojoule is equivalent to almost 5 kilocalories. It's not a whole lot of energy when you think about it. So that is 20 kilojoules. The 5 kilocalories can heat 1 liter of water by almost 5 degrees. If it's exactly 5 kilocalories, then it will be 5 degrees C. So it's not a very much energy. An alkaline battery, AA alkaline battery, has almost 13 kilojoule. If you want to spend more money and you buy AA lithium battery, that will have 31 kilojoule. So when I'm to talk about my equipment that I have, I said we have 20 kilojoule energy. It's not huge amount of energy. However, you need to differentiate between the energy and the power. I have 20 kilojoule. If I have this 20 kilojoule, that's my amount of energy. If I release it in microseconds, then you divide that energy by the time it gives you the power that we're generating. So the power is very high because we're releasing the energy in a very short amount of time. In case of a battery, you are having, say, alkaline battery 13 kilojoule, that you are releasing this energy over many, many hours. So the amount of power is very small there. So let us look what we are going to do. I'm going to describe what we have here, then I will show you the equipment in a second. Basically, I get capacitors, and we store energy in those capacitors. How do I store energy? I plug them into the wall plug, just electricity, regular electricity, the 110. It takes a little bit of time, not a huge amount of time, by the way. It takes just a few minutes to go to that 20 kilojoule. My capacitors I have, they can store up to 20 kilojoule. So I plug it to electricity. If one can design those capacitors to be plugged into a higher input electricity, and you can charge it in seconds. So it is possible to charge those capacitors in seconds. Here we just in a minute or two they are charged. And then we release, by the way, before I leave that, those capacitors are not any capacitors. You can't go off the shelf and buy them. There are very special capacitors that can be used in developing weapons. So we obviously, in order for us to get them, we have to describe to the company we bought it from who we are, and that they are going to be at University of Houston. They will never leave the department. They definitely will never leave the country. Yeah. So you store this energy and you release it, as we are going to see in a few minutes, in just microseconds. Yeah. And those will that create a very high power. And you have two electrodes, and basically I'm passing the electricity. These two electrodes, fairly thick wires, you are going to see them in a second. And I'm connecting them with a very fine coil, basically aluminum wire, but it's very thin aluminum wire, so you can generate enough resistance. You have the electricity moving through it. Basically, that wire is going to eventually explode. Will eventually explode and giving you even more energy. It becomes more like a fuel to that fire, and that creates a plasma bubble that is going to create shock wave on the rock and breaking that rock or separating the grains, which improves the permeability. One can use different material in fusible link. The link that we are going to explode or reduce thermite reaction, as we'll talk about in a second. You can use aluminum, you can use iron, you can use magnesium. Magnesium is not a good idea because it can burn by itself in water. So or you can even use gold. Obviously, gold is too expensive. We'll never use that. So we have been using basically aluminum, but we are planning to use some, compare it to iron and to copper too. And once you have this electricity and you're not just burning the aluminum, but also evaporating that aluminum, you have a thermite reaction of the wire with water, which creates this high energy. If you burn 1 gram of aluminum, it's going to create 30 kilojoule. So you can see you're putting enough energy to start the igniting the wire, and you end with higher energy. So I'm not getting something out of nothing. It is like when you put gasoline in your car and you start the engine, the gasoline burns, is giving you that energy. This is basically the same thing, except you're burning aluminum. When aluminum burns, the basic reaction is like what I'm writing here. you end with burning aluminum with water, you get aluminum oxide, and you get hydrogen, and you get energy. And it's produced very quickly. Basically, the wire will burst. And that you're, as I said, 1 gram will produce about 30 kilojoule. So you put some energy and you're getting a lot more energy in burning that aluminum. The equipment, the basic equipment looks like this. There are two parts to it, some electrical and some mechanical. And I will tell you why. Basically, I have a container like this where you connect all the electrical connections to it. When you open it up, you see something like this. These two are the capacitors. We bought them from a company called Atomic General. You can see that you obviously very special capacitors that can release energy in microseconds. When we have this area here, this is the spark gap where you reach in a time where you said fire it, and boom, it fires. It generates that current, and we're talking about maybe 20 kilovolt, and maybe also about 20 or 30 kiloampere. So it's a very high voltage, very high ampere, very high current going through those wires. It goes in here. I'm going to show you this container here is to make sure everything is safe. But if I remove that part, I hope you see my mouse. This part here is what I'm showing in this picture upside down. So basically everything gets tied in. Inside I have these two electrodes passing electricity, and I have the connection here, this coil where electricity, as you can see, is very thin. If you use very thick wire, of course nothing happens. It moves through it. It may melt it, but it will not burst. So it has to be thin enough to be able to react with water. So when I turn this in here, it goes into a sample like, first let me show you a sample like what I have here in the extreme right. It goes in, I'm filling it with water, and it's inside this triaxial cell. The triaxial cell basically looks something like this, and it has platins. Some are solid platins, this metal here, and there's two more that in with this side and in each of the other sides. And these two platins they can move a little bit, basically to apply stress on the rock. And similar platen at the very bottom, of the triaxial cell. So this applies. This is true triaxial cell. I'm trying to. This is true triaxial cell because I can control the stresses. You can see here there are 3 hydraulic pumps. I can control the stress in X, Y, and Z. So many times, unfortunately, the language in all industries, sometimes people talk about triaxial cell, but what they mean is vertical stress and overburden from the outside. This is not the case. This is actually true triaxial cell, so I can have sigma H min, sigma H max, and sigma V. So you have the 3 stresses. So once I load everything, it looks something like this. I have my electrodes are going in and just fire it. we can look at the effect of stresses. We can do it without stresses. So you can study the various things. And you want to monitor, obviously, you want to monitor the current, you want to monitor the voltage, and you want to monitor pressure also. And so all of that, we have oscilloscopes, we have various equipment to be able to monitor what is going on. To trigger it, to trigger the system, you don't want to be standing beside it, obviously. Although I have to say, since everything inside Triaxial Cell, and this is it's very safe, but we still don't want anyone to be standing there. So you have you trigger the system is standing some distance away, or you go outside the lab and trigger system from outside the lab. But we've been running experiments like this for some time. We never had any problem. So let's look at some of the results and some of the calculations. Well, in this case, we ended cutting the sample because we're going to look at sideways. And you can see in this specific case, we don't put too much stress on very high stress. So this is saying the stress in this direction is 200 psi. This, let's say, I call it north-south. And east-west is 250. And the one here is showing the circle with a point that is perpendicular to the sample. It's 300 psi. If this was a hydraulic fracture, your fracture would have been perpendicular to minimum stress. Minimum stress is coming north to south, so your fracture would have been going east to west. However, in this case, since the stresses are the pressure we're creating is very high, so the stresses are nothing in comparison. So it ends being controlled by perforation, by any plane of weakness there. And you can see I have fracture going this way. So this is a very nice fracture going. It is closer to the north-south, but I have fracture going in this direction too, one in this direction and one generated this way. We also saw sometimes that the fracture going towards the corners is probably the geometry of the system. So the geometry of the system as well as the stresses will have something to do with it. Sometimes we saw if you increase the stresses very much, you can see reflection of stresses, and we see breaks like the one here. You see, rather than having a break going all the way there, it's actually, it looks like the stresses went through the rock and back again reflected and created a break in here. So it is it's very interesting observations. When I look at the electrical and pressure, electrical data and the pressure, you can see voltage and the current. You can see we started at about zero time here. It went up when in 5 microseconds it was reached maximum, and boom, down, and then reflection again going negative. And negative is not, it means they're going in the opposite direction. It's a reflection. So you can see the current and I can see the voltage. The voltage in 5 microseconds, the current immediately went, there was a sudden increase, went to let us see the voltage going to the voltage, I think we miss place this. The voltage is going to close to 20 kilovolt and the current close to 40 kiloampere. Pressure, again, pressure, this is the reflection of pressure. It's going up to 200 megapascal, 30,000 psi. It's 1 megapascal is 10 atmosphere. So an atmosphere is about 14.5 or 14.7 psi, depending how you want to measure it. So we say this went to 29 to 30,000 psi. So one would, someone may say, well, with this high pressure, it should have blown up everything. Well, it is very local. It is not over a huge area. It's only a very small area, which is the wellbore, and it is so. It is similar. One can talk about perforation. You know, when you create the shape, when you fire shaped charges, the jet at the tip of the jet, it may have 10 to 20 million psi on the shaped charges, but does not mean it's going to explode the whole well. It is like a nail going into say a piece of wood. You hammer it, it goes boom very fast. So this is in a way similar, but it is not the same thing because this is a lot bigger volume with that pressure. So it ends creating a fracture or separating the grains, because as you have the shockwave moving into the rock, it's separating the grain and creating a higher probability. And that's we did the measurements. So I will show it to you in a minute. So this is one of experiments that we ran with only 2 kilojoules some time ago, and you can see we ended. This has no stress on it, so this was just not exposed to any stress, and you can see we're creating fractures very easily around the wellbore. When you do numerical simulation around the wellbore, you can see there is a lot of failure. I don't know, I hope you can see what I'm pointing at. You can see some fractures being created like this. In this case, I have 2 larger fractures. So I'm going to show you a couple of examples we did, and we have several papers. I will forward the papers to Dr. Rami Yunus, and you can make them available to you. They don't have everything I have here because some of the material has not been published yet. This one have been published. You can see here we're trying to run just one single shot, and the stresses were, the minimum stress was 250 psi. So single shot, I took 3 samples, cement samples, the cement that we casted, and we used different amount of energy. So 1, 2, and 3 in this 2.2 kilojoule, 4.3, 6.4. And someone may ask me why you are not having exactly 2, exactly 4, and exactly 6. And that would be a good question. We try to control it, but it doesn't. It is not like a lever that I can control to exactly. We're trying to raise the amount of energy, and so it goes within a range. And so but we monitor, so we know what amount of energy we had. So 1, 2, and 3, you can see this is 1, 2, and 3. We went from 2.2 to 6.4, and because of the presence of the stresses, you can see here it may be starting creating a fracture. It looks like there were more damage. When I look at it, look at what is happening around here. Maybe hairline cracks, not maybe, and you can see the liquid moving in there. maybe a higher permeability, maybe hairline cracks. So when I had 6.4 kilojoule, boom, it fractured the rock. So one of our goals here is to look at the effect of stress, effect of the material, then measure doing the lab experiments, then numerically simulate what we are seeing, so we can upscale it to the field, because eventually we would like to take equipment like this, build it in a field style equipment rather than lab style. So this is the single shot. We're just expanding it more. We did the same thing in sandstone. Let me remove this from here. We bought some outcrops, of course. So I got some outcrops, out sandstone outcrops. Actually, I need to tell you here, just in case I don't get a chance to do it. We did cement, we did limestone, you are going to see it, and we did also shale. I don't think I'm showing any of the shale samples here, but shale was very, very interesting too. So here with sandstone, we tried single shot, and we did it also with limestone. And you can see with limestone is interesting because you can look at the fracture. They don't go straight, you go around. They more controlled by not by the stress at all, but by the local changes inside limestone, because limestone may not be as homogeneous. Actually, when we have dual porosity limestone or carbonate formation, which is limestone, we call it heterogeneous formation. So with sandstone, like I'm showing you here, it goes more straight, like looking at the cases here. It goes, once it creates here the coming out of a perforation, it goes fairly straight. But in limestone, and the amount of energy was not, in this specific case, was not very high. So even in here we have, in limestone we use single shot. You can see this case here. This is around the wellbore, the multiple fractures that are being generated, which is similar to when you do hydraulic fracturing and you have very heterogeneous formation. Around shale, things like this would happen. Here we are seeing it even in this shockwave stimulation. So I'm just showing you this one. It caused a lot of damage around the wellbore. There was no wellbore here, and there's no casing. In the cement situation, we did have casing, and that's one thing we are working on, is to look at the effect of perforation. That's one of the things that we're starting to work on and want to study. And this is the other fracture. When you have multiple shots, and what we did in here, we decided to see to put have perforations basically 180, and we do it in align the perforation sometimes with the maximum stress, basically perpendicular, so the fracture will be perpendicular. Minimum stress will going out of the perf is like what you do in the field when you perforate 180-degree scheme. So when I wanted to align it with the maximum stress with perforation, or perpendicular to perforation, to see what happens and whether they are important or not. And you can see here this was the minimum stress this way in this case, and the fracture is actually in here came out 2 fracture perpendicular to minimum stress, so that looked good. But I had also another fracture that went in different directions, so it broke around that wellbore, around the casing, and propagate it in this direction. So you may want to ask me, what is this casing made of? That is just PVC pipe. We have not used it with iron or metal casing. We worry about the electricity and the casing. And so we're using PVC pipe, something that is not conductive to electricity. And then we have maximum stress orthogonal to perforations, and which you usually don't want to do that, and you can see right away things are really funny. And so stress obviously got something to do with it. So now this is the exam, the quiz. I'm just joking with you guys. It's not a quiz, but you can think about it. We ran experiment one time with the rock. The sample was totally saturated with water, and one was not. So the one sample, we saturated the sample completely with water before we ran the experiment. The other one, we just put the water inside the well bore. Which is which? You can see that you can see the two situations obviously produce different results. And I have to tell you, it is maybe opposite to what you think. Actually, the one that was not saturated got smashed all over to million pieces. Well, you know, when I say million pieces, I'm probably right, because those are the bigger pieces. There was a lot of basically sand. That rock was broken into grains. The saturated actually stood up the stress better. So that tells you something about if you're going to apply to gas reservoir or liquid reservoir. The effect of wires, you know, with wire you get something like this. Without wire, you're in situation this way. Effect of rock type, you can see sandstone samples as you probably get. It's a homogeneous formation. You get more straight fractures, not two fractures. It'll be multiple fractures, especially if you don't have a casing. But in limestone, you can see it fractured along the planes of weaknesses. You can see fracture like what I'm pointing at here, horizontal fracture. So you get all kind of things. So this is sandstone with multiple discharges. You can see stress. The confining stress has a very strong effect on those experiments, and we're trying to figure out exactly what is going on. I have some ideas in mind. We all, with my students, you know, we're trying to see what is happening, and simulating this, taking it to field size would help us very much. But as you can see, the amount of energy that is required to fracture the rock increases as the confining stress increases. That does not mean that this is going to be the case in the field. So that's something we are studying with. So what did we do to quantify some of that? Although I'm calling it damage, I probably word damage is not a good word. Maybe I should induce the changes. I should have done that. I should have changed. But anyway, we took a sample that we applied one shot and multiple shots, and we have multiple samples that were studied. And one of them, I'm going to show you results of one of them. Basically, we cut it into pieces, and we took it to look at it visually. We did the CAT scan, and then we took cores out of it, and something like this, and we measured permeability. Most of that amount of work was a huge amount of work, and was mostly was done by ExxonMobil, by Dr. Peter Gordon. And so look what we did. We know the stresses, we know everything. We got, as you can see in the left-hand side, we got plugs, and we measure permeabilities, the permeability values on those plugs. So we found out that we change permeability sometimes by a factor of 10 or even higher. So we decided to do some simulation. So if I say I have not done anything, and we measure permeability of the original sandstone, and it was a very good, fairly good permeability, okay? So I said, okay, if we do this, if we improve permeability that far into the formation by the amount that we measured, we find out that our productivity would, so that's numerical simulation, our productivity would be a lot higher. It's really good permeability reservoir, but we still doubled the production. But then we said, what we also measured for permeability, we said, okay, you're improving permeability here, but in these plugs, they apply to stress, and we see the effect of stress as with time, or the effect of stress on permeability, I should say. So as you deplete the formation, the permeability gets lower, because your effective stress on the sand gets higher. So if we consider that effect, which we call it here with geomechanics, basically I'm compressing the rock, I'm losing this permeability. If I consider that effect, then as you can see here, you lose some production, but it's still a lot higher than before you do that stimulation. Now, if I have fractures, I did the same thing with fractures, and I saw that a very good increase, more than twice, about 2.5 times increase in productivity. Here I put the fractures, but I did not increase permeability around those fractures. I probably should, the next one is to also say I have both. I improved permeability, and also I created the fractures. And I'm not putting fractures here like the hydraulic fractures, the 100 of feet or so. I'm putting just the maybe 10 feet or some smaller number. You can see that it will have good effect in productivity, both for tight and even reasonable permeability. Then we're starting doing some pressure measurements without a sample in a water tank to see what happens. But we still put the water tank inside that triaxial cell. You know, that's safety concerns. Although I know that it would be no problem, but still we don't want to do that. We want to make sure we are absolutely safe. And you can see here we have this table basically putting the same amount of energy. We're using aluminum. The diameter is 0.06 inch. You buy those wires, and you just make it a coil. Here length was a couple of inches. Like here you have, the first one is 3 inches, then the first 3 inches, the last two were 1.5 inch. When it is that small and that narrow diameter, you basically burn the whole wire. It's 99, basically nothing left. It's probably a little bit left that were connected to the electrodes. If I have 3 inches, I'm burning most of it. I'm actually burning more than 1.5 inches. Because 77% of the 3 inches. So I'm bending actually more than 2 inches. So when we look at it, you look at this pressure. By the way, this is in voltage, but it's indication. The blue is voltage, the green is current, I believe. So you can see. So we can. No, the blue is pressure. So you can see what is going on. You can measure pressure, and the idea is to see what happens every time you fire those electrodes. The idea here behind this is to measure pressure more accurately. It's when you put it in a sample, sometimes it's very difficult to, especially inside the triaxial cell, it's very difficult to measure pressure. It's a lot easier to measure electric current and the voltage because that's what you're connected directly to it. But pressure, you have to have a different probe going through the cell. So it's a little bit, actually it's a lot more difficult to measure pressure. So we do it in the water tank. You can see here. The last part, I want to finish this so I can have time for questions. The last part is electromagnetic waves. We have done good amount of work. I'm just going to touch a little bit on what we've done. We did some measurements in the lab, and I'm going to show you the measurements as well as the simulation. But we also did a couple of things. One is we used the finite element model to solve this Maxwell equation, basically, propagation of the electromagnetic field. So we have a numerical model to do it. That's a commercial model. We use the console for the numerical work. But we decided to do it analytically because what we are watching here is coming out of a line. So we could solve the problem either in a line or a point. And so we went through it. We created a solution, the analytical solution. And you're going to see that we match the data very well, both numerically and analytically, except in a small part. So we'll see why. And so the experimental data you can see here is the blue one. So we measured that in the lab. So it starts high and then it basically is like a sine wave, eventually goes flat. The analytical solution is the brownish color. The match is really good. You know, I know there is a little difference here, but the match is very good. It really deviates at the beginning. Because of boundary condition, you could not impose the boundary condition that the model had. The numerical solution, however, which is this one here, you can see it will give you very good match throughout the whole thing, including the beginning. So forget about the surface current density. This is also a measurement, but what we're trying to match is the rate of change of the electromagnetic wave with the time. And we could match it very well. Analytically, we could match it almost perfectly numerically. I have few more minutes to cover. I will cover that quickly. Something we're starting to do. One of my new Ph.D. students is working on this. So basically, we writing a simulator for shockwave propagation is very, very specialized. So rather than trying to develop our own model, we finally got with Los Alamos National Lab, and we got one of their models. They were very generous in that, and they help us a lot. And we also look at their model and verify what is going on. And so you could put the you could describe the sample you're working on. So here we said, okay, we are going to have a cube, but this is the first results we have here is 2D, so it's actually like a square. But we have started working on 3D, and we're producing very interesting results that is happening as we speak. So the first full 3D results we are getting. We got just earlier this week, actually. So I did not want to include those here because we're still working on it. But it looks very promising. But here is square, so it's a 2D problem, and what we do is we say, okay, your inner boundary condition going from 0 to some high pressure. This is not as high as we usually do, but goes flat for a few microseconds or milliseconds, then it goes down to 0. So you're applying a shock wave, and we actually did a lot of study that we are going to publish very soon. We are going to try to write a paper for the hydraulic fracturing conference, although this is not hydraulic fracturing, but or to ARMA conference, to ARMA, and then we'll publish in a journal. So we're looking at all different boundary conditions, how the system or the behavior of the rock, and then we'll verify it with the experiments. So you saw some experiments. We have a bunch of more experiments that we are going to match with this model. And so here is the condition we have. I'm not going to read all of them because it's already getting late. I have time, but I do not know whether you guys do. And we wanted to put, it's not just the inner boundary condition, but I wanted to look at, we wanted to look at the outside boundary condition. So Mina Khalaf, who's a student that is doing this, he looked at constant stress outer boundary, fixed stress outer boundary. Fixed stress means no strain. Fixed outer boundary, not fixed stress. Fixed outer boundary, basically I say no strain, so it cannot move. But the first one, I'm putting just a 5 megapascal. That is 7,000 psi. No, actually it is 700 psi. So constant stress after boundary 700 psi, no strain. And the last one, you don't have any constraints on it, so it can move. The boundary, the outside boundary can move. And you can see what, depending not only on the inner boundary condition and the outer boundary condition, what happens here. And the one thing that I find very interesting is the direction mostly towards the corners. So that work is going to be continuing not only in 2D but also on 3D. So you can see that the outer boundary condition is as important as the inner boundary condition, till we make the sample maybe bigger and bigger, and we'll see what happens. We may even look at maybe circular sample. I'll let you read this, and in summary, I think in the lab scale experiment, very promising results, very promising application. Scaled up triaxial equipment is an excellent step for field scale prototype, and and will mimic what is happening in reservoir. Modeling of plasma, we're doing it right now using Los Alamos National Labs simulators called the HAAS. I need to thank them for letting us use the model. Modeling of electromagnetic wave. We started the work, but a lot awaits to be done. We actually have done a good amount that we have not published yet, but I am planning to do a lot more in the future. And most important, I would like to acknowledge ExxonMobil for funding the work, and definitely Dr. Peter Gordon for seeing the value of doing this research. And I would like to thank everybody that's attending for being patient with me as I spent over an hour talking to you, ladies and gentlemen. Thank you very much. And I would be glad to answer questions.
Thank you, Professor Soliman. It's time for questions. If you'll raise your hand, I'll call on you. We've got a question from Goyo Chu. Goyo, don't forget to unmute to ask your question.
Does it appear I don't have any questions?
Yeah, his audio is not coming through. Maybe we'll circle back to you, Goyo. We're unable to hear you. We've got a question from Wenkao.
Thank you, Dr. Soliman, for your great presentation. I have two questions. The first, on slide 28. Yeah, I see the fracture seems like doesn't connect to the wellbore. Could you please explain why or correctly?
Well, no, actually, they are connected to the wellbore. In some cases, we had a casing and perforation. So definitely the perfs are connected to the fractures. In some of the experiments, I'll tell you something interesting. Some of the experiments, we don't have casing, and obviously, if you look at it, it broke through the wellbore. I'll tell you one experiment that we ran where we put casing without perforation, and believe it or not, it still fractured the rock. There was no, in that specific example, there was no stresses, and the PVC pipe basically expanded and broke the rock. But yeah, those fractures definitely connected. They are going through the perf and from the perf into the formation. There are some that we did not have casing altogether. They were direct connections. I'm interested that you thought so. Or next time when I make a presentation like this, I will definitely make sure to show a slide where you show a direct connection between the perf and the formation. It's an interesting observation, but I have to tell you, it is connected. I know that because we looked at it.
Okay, thank you, Professor. And another question is, when you break the rock, actually, the mechanical property of the rock, like that's not.
You're coming very broken. Okay, can you repeat and slowly?
Yeah, my question is, how do you think the degeneration of the Young's modulus or other mechanical properties will affect the wave propagations? in the rock?
That's a very good question. I'm going to do. We're looking at it in. We obviously measured the Young's modulus and Poisson's ratio for the sample for the sandstone and the cement. We were looking at running examples where we change the water ratio because sandstone we get whatever is outcrop. We're looking at this issue in two different ways. One in experimental work. Once we match the experiments, then I go back and run the Haas simulator with different properties. Because of course, in order to run it, you need to enter all the mechanical properties of the rock. You know, we basically use Moore circle as well as Young's modulus and Poisson's ratio. So the idea is what we plan to do is with cement is to vary the ratio of water to cement to change how strong the rock is, what's from Young's modulus and Poisson's ratio, shear modulus values. But we have not done that yet. We see very strong effect when you run the numerical simulator.
Okay, thank you, Professor.
More questions for Professor Soliman?
Hi, Professor. Can you hear me?
Yeah, I hear you very well.
Yeah. Sorry for the mic. Thank you for the quite interesting presentation. I have a question about the mechanics of the conducting fracture. Does it because of the pressure of the plasma? I'm not familiar with the plasma.
We are creating the pressure created inside the wellbore. It can be up to 200 megapascal, which is about 30,000 psi. So yes, the answer is you're creating very high pressure, and it's very high power. It's not exactly the same thing, but it's like if you have a piece of china, for example, and you have a hammer in your hand and bang it with a hammer, it's going to chatter. It is not to the same extent, but there's a similar way, because I'm suddenly applying a high power, which is pressure maybe 25,000 psi on that piece of rock. So that's what is breaking it. And it makes if you have a stress orientation, it makes the stress orientation almost unimportant. Similar to what we saw, we're using propellant, which is a similar thing, because propellant also produces very high pressure. It's not like hydraulic fracture, because when you think about it, most people think about hydraulic fracture, you are ballooning the well, you are breaking the rock. This process, when you do it slowly, you're opening the fracture perpendicular to minimum stress, because that is the path of least resistance. Here, those stresses are almost as if they don't exist. Unless, of course, and that is the effect of how much energy you are releasing. If you're releasing a lot of energy, then it becomes almost, it's not like an explosive, but it's it's high enough that the stresses are not important. If you release small amount of energy, then you may not even fracture it. You may just vibrate the grains, where you separate them, where you improve permeability. So in cases where we saw higher permeability, what is happening is the shock wave is vibrating the grains and actually separating them a little bit, that improve the permeability by, in the cases we're looking at, by more than factor of 10.
Thank you, Professor. I still have questions about in your slides. I found that the maximum energy of the plasma is about 12 kilojoule, right? And why could we choose a larger? Because of the equipment. And I want to ask, do you have the relationship with the energy and the pressure of plasma?
Okay, that's a very good question. It's not the equipment is capable of delivering 20 kilojoule. However, you know, like for example, a car may be able to drive 140 miles per hour. That's what you read in the speedometer. But do you really want to drive it that fast all the time? No. Obviously, you get a bad ticket and you get an accident. You don't want to do that. But in equipment, if I'm trying to restrict to it is basically to preserve the life of the equipment. If it's capable of producing 20 kilojoule, I really do not want to use it. We use it up to 12 kilojoule here, but generally I don't use it more than 10 kilojoule because, you know, it has a lifetime, and the lifetime, the capacitors and the equipment have lifetime, and the lifetime is directly related to how many shots you use and how high energy you use. So in a way, I'm trying to save my money because those replacing some of those will be very expensive. You know, the equipment you're looking at are very expensive equipment. You know, there's not is not thousands of dollars. Is many hundreds of thousands of dollars. So
yeah, got it. Thank you, Professor.
There was another question that you had. You said you talked about the amount of energy. You said something else. I can't remember. Can you repeat that? Or
it's about the relationship with the energy and the pressure of the plasma.
Oh, there is multiple things. That's a really good question. We developed a spreadsheet to do these calculations. You know, you want to have the amount of, you want to put enough energy to initiate that reaction, and that amount of energy that is needed to go to initiate it. Not only the amount of energy, it depends on the type of wires you have, whether it's aluminum, iron, copper, whatever. So the type of wire, so the characteristic of that specific wire, you also got to do with the diameter of that wire. And obviously we're talking about a very small diameter, you know, a millimeter or close to it. So the type, the diameter, and the length too. So I can tell you something like almost like a story. When we got the equipment, if you put very thick wire, very short wire, and you put a small amount of energy, it just electricity goes through from one electrode to the other. You can see the electrode, even the electrode is fairly thick. It is at least 3-4 millimeter thick. It is still it gets damaged as we use it, because the amount of energy, that's amount of electricity that's going through it. So the relationship is fairly complex, and in order to do the calculations of what it takes, we created a spreadsheet that takes takes care of all these calculations. You know what it takes to heat it and to melt it and to evaporate it, so you can start the plasma. And then we know how much energy, for example, when in some of the what I showed you, if it takes if you burn 1 gram of aluminum, you end up getting 30 kilojoule. So you put maybe 10 kilojoule in, and you end up getting, if you burn 1 or 2 grams, 1 gram will produce 30 kilojoule inside the wellbore.
Yeah, thank you, Professor.
You're very welcome.
All right, I think we have time for one more question. I don't see any hands up, but maybe I can take this opportunity and ask one. So I'm Professor Soliman. You know, I haven't done experiments since back in the day when I was an undergraduate student. I'm more of a theory person, but the speed of sound in water is a lot lower than the speed of sound in VPVS in rock. So these waves these mechanical waves moving through the rock, are they essentially seismic sort of waves or shock waves?
It is shock waves. It's a supersonic, actually.
Even though the speed of sound in rock might be 5,000 meters a second compared to the speed of sound in water?
Yeah, but this is supersonic. It is faster than the speed of sound.
Interesting, yeah. So I'm aware of the medical, applications of pulsed plasma, this kidney stone removal procedure. And from what I understand, the name of the game in that application is concentrating these acoustic waves, essentially. I don't think they use pulsed plasma anymore. They use kind of an EM diaphragm to deliver the original wave, and it's typically acoustic. But then over there, they try to concentrate, using acoustic reflectors to concentrate these waves onto the calculus, onto the kidney stone.
Yeah,
so
we actually, yeah.
It seems
very
mind-boggling. They can have so much precision, in terms of power, and so I wonder how much technology from the medical field will find its way, into the oil patch.
I like what you're saying. I'm going to tell you something else about something else we are doing. But by the way, we read all the papers that they have on kidney stones and so on and so forth. Ours is a little different, but there is a lot of application in other industries and other fields that can fit very well. For example, we are doing some other research and that research is theoretical. It's not, there's no experimental work on it, where we analyzed data using wavelet technique. Basically, the same technique that came up with. I thought of this idea many years ago. We did a little bit of work about 2003 or 2005. I can't remember the exact time, but more than 15, 16 years ago. But we started reapplying it, and we found interesting application. And the reason I thought about it is the medical field too. When someone goes to cardiologist and does EKG, the heart monitoring and finding whether valve is closing properly or not, so on and so forth, they take this data and analyze the data that you're getting using wavelet transform. So we start applying it to various applications like well testing, like defit, getting when fracture closes when it opens. And we wrote a bunch of papers on the subject. It's extremely interesting. It works really well in all industry and in what we are doing. I'll be glad to send you a couple of those papers too. And we're getting it funded. We're doing more than just that. We're doing that as well as linking it to geothermal reservoirs and production from geothermal, as well as we're building a numerical simulator for hydraulic fracturing that will work also for geothermal reservoirs. So we're building a whole group, but this is theoretical work. But the part that we do in wavelet is very much like what people do in medical field. There was actually a friend of mine that was a civil engineer, was friend from Stanford time, and he started doing work in medical field. It's so interesting that both of us, he and I, published work using wavelet transform. I did it in oil industry. He's doing it in medical field for I can't remember. It was kidney work, kidney analysis of failure of kidney. So it is. We were doing it for fracture propagation, fracture closure, and well testing and defect. So
yeah, that's a great example of cross-fertilization between different fields.
Right, absolutely. I am firm believer in that. I have done some work that actually I have a problem that I solved many years ago, and when I formulated the problem, it looked very complex. So I said this problem must have been solved before, and I look at it and I found same problem. You require translation was done in electrical engineering. I found it in a book. So instead of spending 3-4 weeks solving problems and writing simulators, I found a solution down there.
Great. All right. Well, thank you again, Professor Soliman, for a very interesting and intriguing seminar. This concludes the amount of time we have for the seminar, but I see your email address on the screen should anyone maybe contact you with questions or that sort of thing.
Sure.
All right. Thank you. Thank you all.
Thank you very much.
Thank you. So, Professor Soliman, do you want to hang if you have a couple of minutes
sure.
to stay on the call when people leave?
Okay.
Thank you.
Sure. I really enjoyed talking to your students, by the way.
So I think people are still signing off. Yeah, but I just wanted to thank you once again, and hopefully we get the chance to one day, perhaps do the seminar in person once again.
Sure. Yeah, and if you're in Houston, come and stop by.
Yeah, I would love to. Yeah, that would be great. Yeah. I mean, it's been since COVID. I don't think I've traveled except for road trips here and there. But
me too.
Yeah. So how are things these days at U of H? Are you guys back to in person?
We are face to face now, or
Great.
everything in person. But I have been reluctant to travel.
Yeah,
I did not even go to the annual meeting.
exactly. Yeah, yeah.
I could not. My wife was saying, no, it is not worth it
It's not. Yeah, yeah.
to do
And
that.
anyway, travel is very difficult, even beyond the medical potential medical issues. I mean, I'm scared to fly just to prove vaccination or not and whatnot, across borders. And uh, I think it's going to take time before, especially international travel, really comes
Yeah,
back to normal.
I when I worked for Halliburton, I used to travel way more than 100,000 miles a year. I used to be out of the house 100 days, 110 days per year,
Wow,
all
yeah,
most national travel. After I
yeah,
moved to academia, it declined some, but now during this last year, I did not go anywhere.
right. I keep thinking about, like the air miles, and before, and now it's kind of all, in my case, gone to
Yeah, yeah.
scratch. Great. Yeah. By the way, incidentally, on this topic, I I work, it was a couple of years ago. We're in our third year now. We secured a DOE project from fossil energy to look at the interaction of seismic waves with hydraulic fracturing. So it's my colleagues at OSU, they're material scientists, and what they
Mhm.
wanted to do was hit, um, if you have a frac job, hit fractures with seismic waves as they're propagating, to
I
try to
have a
see.
patent.
Oh, you
I have
do?
I
Okay.
have a
Yeah.
patent on using this technique here with hydraulic fracturing.
Yeah, to try to kink the fracture, change its direction or branch,
Right,
that sort of thing.
right,
It's kind of
right. I
interesting.
have a patent on. I'll be glad to send you the patent.
Yeah, that would be great. They're looking at it like from a material science, standpoint. But I'm involved with the modeling side of things. Uh, but in that case, it seems I think almost like you would rather do what you're doing with the pulse and then follow it up with some high pressure injection or something.
Well, in my patent, what we say, we actually coupling two things with hydraulic fracturing. Is we developed the technique which we are expanding right now, by the way. It's called the moving reference point.
Mhm.
Uh, we developed this technique when I was in Texas Tech. Basically, you can analyze the data, and with the analysis of data, you would know whether you're getting into sand out or you're intersecting natural fractures.
Mm, mm.
And if I have, you see, if you change rate at the surface, by the time you get an effect at the tip of the fracture,
Yeah,
it's already too late. It takes too long, and the
yeah,
effect is very much muted.
yeah,
However, if you have something like this pulse power downhole and
yeah.
you apply a pulse, that pulse goes even inside the water 5,000 feet per
Much
second.
faster.
It
Right,
reaches the tip of the fracture in a fraction of a second.
right. Yeah.
So
It's
the,
it's it's almost like, instead of microseismic, which is passive, you're waiting for the fluid rock interaction to happen. You're
right,
putting an active seismic and you're hitting it with stimulation waves so you can.
right. That is,
Yeah,
so I have the patent. It got issued a couple of years ago.
great.
I can say I will send you the patent. You will.
Yeah, that would be great. I'd appreciate it. is it okay if I share it with these colleagues at OSD?
Yeah, it is.
It's mainly their
The
project.
patent, anybody can go into Google and type my name and the patent, you can get it.
Great.
I will send you the patent.
Great. All right. Well, thank you for being so generous with your time once again. And you know, it's a true pleasure meeting you, albeit
Thank you,
virtually.
Thank you.
Yeah.
Hopefully, we'll see you sometime.
Yeah, I hope so too.
All right.
Thank you, Professor. Thank you.
Thank you, sir. Okay. Bye-bye.